The magnetic moment. Okay, so classically, if you have a charge, for example here, this charge, positive charge, Q larger than 0, is rotating in a circle, right? And it has a mass, okay? Let's do not talk about the charge first. You have a mass. Then you will gain angular momentum. That is the first thing, right? So you will get L is the angular momentum. Agree, everyone? Something spinning has angular momentum, so it's not easy to flip it, right? Like the top is spinning, it has angular momentum. If you want to flip it, you actually need to change its angular momentum. So that's why it's not easy to do that, because you need to apply enough force to change its angular momentum. Instead of linear momentum, we're talking about angular momentum. Make sense? Now, but if that particle also has charge, it also at the same time will develop something called magnetic moment, mu. Not all of us still remember what we learned, or even if we have learned this in our more elementary physics class. So you don't need to feel uncomfortable, but you need to just take it for granted. Just like people tell you that something moving fast has a larger momentum. This one you can accept, right? Now I tell you that if it's spinning fast, it has something called angular momentum. Accept it if you forgot. But it's great if you can go back to study again. Same thing, if it has a charge, it also develops something called magnetic moment. So this is from classical electromagnetics, right? But more importantly is that classically, there's a relationship between the magnetic moment and the angular momentum. That the angular momentum equal to gamma times the magnetic moment, the angular momentum. The magnetic moment equal to gamma times the angular momentum. And this gamma is a very important parameter, which we call it the gyromagnetic ratio. Okay. And basically say that if you have a large angular momentum, you're going to have a large magnetic moment. Okay, we accept it. And classically, gyromagnetic for electron, no, not for electron, just classically. Classically, the gyromagnetic ratio equals to the charge divided by 2 times m. The mass, okay, this is the Q is the charge of the particle, and m is the mass. That is the first thing. Okay, so here we introduce two things. Angular momentum, I hope you're okay with that. Spinning thing has angular momentum, and they have magnetic moment. And they are related by the gamma gyromagnetic ratio. You don't need to memorize this equation, because this will be gone in our study in this class, because this is a classical relationship. You will see that it's actually Q over M later, right? So, but this is just for you to do some comparison, because you might read something like this, right? Now, you see that this is also a vector. When it is rotating, how do we determine the direction of angular momentum? We use the right-hand rule, your thumb, right? You thumbs up, then your other fingers represent the rotation direction, and then the thumb represents the direction of the angular momentum. You see that when it is positive, the angular momentum and the magnetic moment are pointing in the same direction. When it is negative, they have the same mass, right? They are rotating in the same way. So, of course, the angular momentum is pointing also up, but the magnetic moment is pointing down. Make sense? So let me ask you, is it positive? What is the sign of the gyromagnetic ratio if the charge is positive? Positive. Because based on this equation, you say that you are going to point in the same direction. If it is positive, so then gamma needs to be positive, right? When it is a negative charge, what is the sign of the gyromagnetic ratio? Negative, thank you. I know this is very trivial, but you need to. Any questions about this? And it also makes sense if you look at this, gamma proportional to Q. If this is positive, then I have positive gamma, right? If the Q is negative, then I have negative gamma. So this is something very important for us to understand the spin and magnetic interaction. Any questions? So we have learned angular momentum. We learned magnetic moment. We even don't know what it is because that need to spend a class, right, to understand all this. But we just accept it. Yeah, just now you accept something has charge, okay? But you need to know their relationship. And I give you the classical background. You can go back if you're interested in it, read it, and understand more. Now, if a moving charge has angular momentum, then what if I have a large body which is spinning? Does it have angular momentum also? If something is spinning. Yeah, you can call it, let's don't call it spin angular momentum for now. Yeah, but it's spinning, right? It's just like a big ball, a basketball. When it is spinning, it has angular momentum also, right? Now for elementary particle, they also have something called spin, but they are not really spinning because electron is a point charge. Quark is a point charge. You cannot say that it is spinning like a basketball. The reason basketball has angular momentum because the molecule outside are really rotating, right? So you have this angular momentum. But electron doesn't have. However, it has a property, spin. Spin is something like a property of a particle. It's not really spinning. Imagine that there's a kind of animal. They cannot feel the charge. Or no, even ourselves. We don't know the charge at the beginning. And suddenly we discover there's something called positive and negative charge. Have you ever questioned what is the meaning of positive or negative charge? I bet most of us have not. I have not neither when we learn it. We accept it. It's just a characteristic of the particle. They say electron has negative charge. What is negative charge? Proton has positive charge. What is positive charge? Of course, when you go to very deep, the mathematician tell you what is the meaning of charge, right? But I don't know. Same here. Spin is just a property of the particle that we didn't know before. But then after you've done all this experiment in the 20th century, they suddenly found out that those particles have an extra characteristic parameter called spin. Then why the scientists are so troublesome? While it is not really spinning, they call it spin. Because at night it is spinning. The reason is this. There is some, first of all, spin can have a value that is either plus or minus half. That is first of all. They did the experiment. No matter how they measure, it's plus minus half. Okay? And then they realized that also when a particle has a spin, it also has spin angular momentum. Which is a vector equals to S H bar Z hat. And that's why they call it spin. Because somehow this particle has angular momentum, although it is not moving. That is the point. So as this electron is spinning, but again, electron is a point charge. Even you're spinning, you should not have angular momentum, right? Because it's zero. You always at zero coordinates, you don't have angular momentum. So in reality, it is not really spinning, but we call it spin because it gives angular momentum. And the value is the spin times the reduced Planck constant. Okay, and now let's just say it only point at the z direction because the way they detect it is through applying a magnetic field to realize that whether it has spin up or spin down. And you will realize that it will be like at z direction, right? So let's don't go deep for now. Later we will understand better. Similarly, it also found that when you have spin, you also have a spin magnetic moment. Right? It's a physical property. You can measure it and turn out this spin magnetic moment is just equal to gamma times the spin angular momentum. With gamma, equals to G E divided by 2m. Here I only talk about electron, okay? Where G equals to negative 2.0023 and they can keep going. So now the scientists trying to determine the exact value of G, and this actually related to how much dark matter we have in universe. I went to a seminar, I don't understand, but they told me that is how they do it, okay? So the value of G is going to have a very big impact to this universe composition, but we don't care. So that's why here, are you trying to derive it? We cannot because we just take it as granted. So now you probably understand why it is called spin. Because the spin, every particle has a spin. It has a spin angular momentum equal to S times H bar. It also has a spin magnetic moment equal to the gyromagnetic ratio times the angular momentum. While it's actually not spinning, it is not spinning because it's a point charge. And that's why it is called spin. And that is what confuses us. But that is a very valid reason to call it spin because it acts like it is spinning. Okay? So at this stage, all you need to know is, yes, spin, we only talk about spin half particle. They are different particles. Some have integer number. Some has up to plus minus 3/2 by plus minus 1/2. Now we talk about spin half and also limited to electron and proton and hole. So they only have two spin value, plus minus 1/2. And these are their spin angular momentum and spin magnetic moment. Now you see it has two value. What comes to your mind right away since we are talking about quantum computing? Yeah. It has two basis states. So this will be a very good qubit because you can either spin up or spin down. You cannot have plus 3/2, right? Okay, so that's first thing. Good. And let me just introduce also, if it is proton, it also has the same equation, but the G is 5. I got this from Wikipedia, should be correct, 5.586. So you see this gyromagnetic ratio is very different. I want to get your attention. For electron, G is negative. Okay, here E is the charge for electron. Let me make it clear. E equal to 1.6 times 10 to the power negative 19. This is the elementary charge, not the charge of electron, just elementary charge, so it's positive. So Is gamma negative or positive for electron? Negative, because G is negative, right? Now G is about 2. So 2 is to cancel 2 very soon. Then you get E over M, approximately E over M, right? The gyromagnetic ratio. But classically, it is E over 2M. Also, this is something people always mention when they study this from classical to quantum. This is due to the property of spin. It's just because the spin is 1/2. If it were not 1/2, then that will be different. But anyway, after all, you can forget this slide. We're not going to test it, but just link you to classical. Most important is now you understand for an elementary particle, you have spin. And because of spin, you have spin angular momentum. And because you have charge, you also have spin magnetic moment. And you have this equation, which you should put in your cheat sheet if you cannot memorize. Okay? Now, then let's just talk about a very important quantity called Bohr magneton that you will see very often. You don't need to memorize. It's talking about the magnetic moment of electron. But of course, it's absolute value. So what is that? It's equal to GE divided by 2M, which is gamma times, sorry, let me do it again. So it's equal to magnitude of gamma S, right? And gamma is just GE over 2M. And what is S? S is H bar times S, right? But S is 1/2, correct? Because the spin angular momentum is S times H, right? And S is plus minus H, plus minus 1, plus minus 1/2, the spin. So it's spin, or now maybe you should memorize it. Spin angular momentum, just H bar over 2, plus minus H bar over 2, right? For electron. So what is this? Because G is about approximately 2, right? So this one you get this. This is the so-called Bohr magneton. Okay, we label it as mu B, right? But this is a scalar, right? Not a vector. This is just a value. That is what you can have with an electron. Any questions? So we know we have spin plus minus half, spin angular momentum plus minus half H bar, and then spin magnetic moment further multiplied by gamma. Okay, three things: spin angular momentum, spin magnetic moment. And what really important is the interaction of spin in the magnetic field. So if you put the electron just in an isotropic space without magnetic field, you really don't know, right? Imagine the universe doesn't have anything. There's no up, down, no left, right. Because you cannot distinguish, it's isotropic. Every direction is the same. So naturally, spin up or spin down should give you the same energy because you cannot distinguish them, right? So under zero magnetic field, spin up and spin down will be the same. Is that okay? Now then, let talk about one more thing that I just say that if you are spinning, then you have the angular momentum, right? Think about classical one. When you have positive charge, then the spin direction and the magnetic moment, and the angular momentum and the magnetic moment should point in the same direction. What I'm talking about is this one. If you're spinning, like this is not spinning, right? But you have angular momentum, right? The angular momentum L will point in the same direction as the magnetic moment when it is positive charge. So that's why when you spin up, the magnetic moment is pointing up. also. Any question? This is very important. Make sure you understand what I'm talking about. Any questions? Okay. So when it is a positive charge. When it is a negative charge like electron, if I spin down, what is the direction of the angular momentum if I spin down? Angular momentum. When I say I spin down, it basically just saying that it will be the same as the direction of the spin. Right? You just think about spin, although it's wrong, but think about spin as a mechanical spin. Right? So the spin direction will be the same as the angular momentum direction. Right? Because when use right hand rule, right? If I'm spinning in this way, then this means that I spin up, because the definition of spin up is like this. So it is pointing up, right? So when it is positive charge, I spin up, the angular momentum is pointing up. At the same time, the magnetic moment is pointing up because the gyromagnetic ratio is larger than 1. Now, if I have an electron that spins down, what is the direction of the angular momentum that you are moving? If I spin down. What is the angular momentum? Same direction, because spinning, just think about mechanical. It is wrong, but think about mechanical. So it is angular momentum pointing down, right? But how about the magnetic moment? It should point up, right? Because the gyromagnetic ratio is smaller than 0, this gyromagnetic ratio is larger than 0. Okay? That is the first thing. Now, if I put up a magnetic field, look at this magnetic field. It's pointing at the z direction. B0 is positive, right? So it's pointing at the z direction, okay? What will happen? You will get something called Zeeman splitting. Okay? The reason is because you will create a Hamiltonian H equals to negative mu dot B. Again, we will take this for granted, right? We are not going to derive the equation or whatever. The energy change is equals to the magnetic moment inner product with the magnetic field, the scalar product. Okay? Maybe it's a little bit confusing, right? But let's look at it. What does this mean? This is equal negative, the magnitude of the magnetic moment times the magnitude of the magnetic field times cosine theta, which is the angle between these two vectors. This is inner product. Any questions? Really slow today. Okay, so let's take an example. Because you don't respond, I assume that you don't get me. So please let me know if you. For example, if mu is pointing up, B is pointing up, it means they are parallel. What is the angle between them? Very good. Theta equals 0. What is cosine theta? So this 1h equal to negative mu B. Right? Because cosine theta equal to 1. Now let me use another color. Mu is pointing up, but the B is pointing down. What is the angle between them? Thank you. This is anti-parallel. And I have theta equal to pi. And what is cosine pi? Negative 1. So the Hamiltonian equals to mu B, which is positive. And this is negative. So basically it's saying that if they are parallel, you actually increase the energy of the system. because Hamiltonian is positive. If they are, I say the opposite. If they are parallel, you decrease the energy of the system because it is negative. You add negative energy to the system. If it is anti-parallel, you increase the energy, right? So let's look at this. Before I put any magnetic field, spin up and spin down have the same energy. You cannot distinguish them. When I set up the magnetic field up, when my magnetic moment is up, they are in the same direction, right? So I actually reduce the energy of the system. But if my magnetic moment is pointing down, then now they're anti-parallel, I increase the energy of the system. Is that okay? This is the same for electron. Let's only look at the magnetic moment. When they're parallel, right? Magnetic moment pointing up, magnetic field pointing up, I reduce the energy of the system. When they're anti-parallel, I increase the energy of the system. But the only difference is what? For negative charge, when my magnetic moment is pointing up, my spin is pointing down because my angular momentum is also pointing down. Okay? So a little bit troublesome, but eventually then you will see that when I set up the magnetic field up, for hole, if it spin up, I have lower energy. If it spin down, I have higher energy. And that is how you distinguish these two qubits. For electron, if I spin down, I have lower energy. If I spin up, I have higher energy. That causes this so-called Zeeman splitting. Okay? In our class, from now on, we are going to set up the experiment in this way. We are going to set up the magnetic field pointing down. So where I have negative B0, where B0, of course, need to be larger than 0. Negative Z direction. Okay? Now let's just ask ourselves again, and only care about electron. Let's look at this again. What do we say? We say if your spin is opposite direction of the magnetic field. I'm talking about spin, not magnetic moment. You have lower energy, right? So as a result, here in this setup, spin up, which I call it the ground state, will have a lower energy. Spin down, which is the excited state, it has a higher energy. This is just a convention. Some people might swap it, but we decided to do it in this way. This is the ground state. And this is the excited state. Is this okay? Okay. Now, I know it's confusing, right? But after all, I just want you to know that you have this confusion in the sign. So you need to be careful. You don't need to memorize it. But when you use it, you need to be careful. And now our system is just that we are pointing down in this class. It depends on textbook, depends on experiment or paper, how they set it. Now we are pointing down. So for electron, top has lower energy. I call it spin up. The bottom has a higher energy. I call it spin down. Okay, and this is the broad sphere embedded in our system. Okay. So with this, then let's start construct the Hamiltonian. Because if I can construct the Hamiltonian for this spin system or the electron spin in an external magnetic field, I will be able to solve the Schrödinger equation. If I can solve the Schrödinger equation, then I know how the qubit state evolve. Okay, so the first thing is to construct the Hamiltonian. For the experimental setup, I'm not going to say this again. Oh, then, so I need to say it because it can be confusing. Just make sure that it is the magnetic field is set up as pointing down, negative B0 Z hat. Now I have this one here. This is not the setup, okay? Not the setup in this place. This is just for you to recall the energy level. This is not the setup here. Okay, this is not the setup, right? But here just tell us that I want you to see that for electron, spin down, if the spin go in the opposite anti-parallel with the magnetic field, you have a lower energy. That's the purpose I put the picture here. But here, remember, this is our setup. Our setup is the magnetic field pointing down. Okay? That's first thing. Second thing, based on experiment, tells us that there are two eigenvalues or two possible outcomes. Let me call it possible outcome. Possible outcome. Right? Corresponds to the two eigenvalue or energies of the Hamiltonian. Right? So we have this set up. We do something, try to measure the energy difference between. You just keep doing measurement or whatever experiment. You realize that if I have the magnetic field pointing down, I try to measure its energy through whatever method. I always only get two values correspond to spin up and spin down. Okay, and so this value must be the eigenvalue of the corresponding operator, which is the Hamiltonian, right? And what are these values? These values are when I sometimes measure negative mu dot B. I mean negative mu B, I should say. Negative mu B for spin up. Or maybe let me erase A. I only get two values, and let me call this actually lambda 0. Lambda 1 equals to mu B for spin down. Right? This is what we already discussed. I already told you the Zeeman splitting is going to change the energy by negative mu B and mu B. Right? And why do we need that? Know this? Because either some more fundamental theoretical calculation or just based on experiment. I only have these two values. Okay? So these are the eigenvalue of the operator, which is the Hamiltonian. And then base what we know before. So for spin up, let me call it 0. For spin down, let me call it 1. So I can construct the Hamiltonian matrix, right, which is summation I equals 0 to 1. This one we learned that before is lambda I. A little bit similar to what we have just done now. To construct the matrix, right, we go through all the row and column and then the elements. But because this is the eigenvalue, so we only need to go through the diagonal because the rest are 0. Okay? So, but we talked about this before, right? This is a special case of what we just taught. But earlier we already said that to construct the matrix from its eigenvalue is just the eigenvalue times the corresponding outer product of the the eigenvectors. So let's practice this. This is equals to, what is lambda 0? This lambda 0, let me write it down. This is equal to lambda 0 times the outer product of 0 lambda 1 times the outer product of 1. And what is lambda 0 in this case? Negative mu b, and then zero, zero, right? And times mu b 1, 1. Correct? But what is 0, 0 outer product? It's a matrix. Do you remember what it is? 0th row, 0th column. This one. Here. Like this. 1 to 0 is like this, right? Then 0, 0 is just 0th row, 0th column, right? So basically, this is just equal to negative mu b 1, 0, 0, 0. Mu b 0, 0, 0, 1. Okay, then let me just take out the factor and add them together. What is this matrix? First of all, is it correct? I factor this out, factor negative mu b, right? So this becomes negative 1, and I add them together. What is this matrix? Sigma c. So turn out this Hamiltonian has the poly sigma z as its matrix is formed, right? So here I can further say something, because this mu, I already know what it is. The mu b, just note that mu b is the Bohr magneton, right? So this is just also equals to negative E h bar divided by 2m times b0, sigma 0. Because this is just equals to the negative Bohr magneton times b0 sigma 0. So if we go back to this Bohr magneton, it is EH bar divided by 2m. This is EH bar divided by 2m. Right? Because it makes sense, we're talking about electron, then of course its magnetic moment is the Bohr magneton. Approximately. Right? Because G is not actually negative 2, it's 2.002 something. Right? Any questions? Good, so we have this, fine, right? So now we have the Hamiltonian. This is the Hamiltonian of the spin, of the electron with spin, under a constant external magnetic field B0. Okay, we have it. Then let's keep it aside for now. Let's